In this video, we're going to talk about coding of variables and using Levene's test. So Levene's test is one of several different tests that you can use for checking homogeneity of variance. That is, it's testing to see if the variances are the same across categories. This is an important preliminary step in doing all kinds of other statistical tests, especially in analysis of variance. MANOVA, also in regression. Of course, we want to check to see that the variance of the residuals is uniform across the explanatory variable values. So, but to do that, if you're in the context of regression, you've got to be able to carve up your explanatory variable values into groups or categories, because Levene's test won't look across an entire swath of values. You've got to carve it up into categories and compare the variance of whatever response variable, or in this case our response we're really looking at the residuals, so that you look at the variation in that variable versus the category. So I'm going to pull in a data set from that goes along with the problem in your book. It's chapter 3, problem 18. I'll read this to you real quick. In a manufacturing study, the production times for 111 production runs were recorded in this here table. The table lists the production time in hours and the production lot size. Okay, I'm also going to give some names to these variable values and check out the first few rows. So here we've got production hours, and in this column we've got lot size. There are actually 111 rows here in this data set. Okay, now very quickly I'm going to plot production hours versus lot size and also do a regression line. Okay, you can copy and paste that into R, and there you can see that in fact there does seem to be sort of a quasi-linear trend. I bet our R-square value is something like 70 or so percent, maybe 80%, maybe more. And in fact, I guess you can see what that is. Summary out. Yeah, okay, 0.74. So that says that the proportion of variation in our response variable, the up-down variable, the proportion of variation in that variable that's captured by this model line, this regression line, is about 74%. Okay, so that's probably pretty good, I think. Of course, these two numbers are our slope, this is our slope coefficient estimate, and this is our y-intercept or vertical intercept estimate. Our p-values are super small, indicating there's statistically significant evidence suggesting that these numbers or that these actual beta values are different from zero. These are not the actual betas. Remember, these are estimates for the betas. Up here we see some statistics about our residuals, and that's what we're mainly concerned with in this video. We want to check out the distribution of these variances, and in fact we want to sort of check to see if these variances if the variances in the residuals change as you move from left to right. Okay, as you move along this line, does the variance increase or decrease? It's kind of hard to tell. It looks like there might be a little bit of an increase here, but I mean, if you threw out these two values, then maybe not. We're just lacking some lot size data over here. It'd be nice to see some more lot sizes that were up here around 25 or 30, but so it may be kind of hard to tell if the variance is the same. But but I'm going to use Levene's test to sort of to do sort of a naive check about that. Here's what I'm going to do. I partition my lot size variable values into 3 categories. I'm going to go from 0 up to 10, and then from 10 up to 15, and then from 15 on up. Okay, so that I'll compare the variance of these the residuals of these values with the variance of the residuals of these values with the variance of the residuals of these values over here. Okay, so so I've got to carve up these lot size variable values into those 3 sets. There are several ways to do that. I'm going to use a sort of an archaic way, using a loop first, because I think you should know how to run some loops in R, and then we'll do it a quicker way. Okay, but so here's way one. I'll say first of all, my counter is, I'll say I'm going to initialize my counter with 1 there, and I'm going to write a while loop. Okay, so while my counter is less than or equal to the number of rows in my data set, I'm going to do the following. I'm going to use if-else statements here, and I want to basically say if the element in the ith row, column 2, right, because we're partitioning the lot sizes. If I is 3, if my counter happens to be 3, if this value falls at less than 10, I want it to be labeled low. If it falls between 10 and 15, including 10, not including 15, I want to be labeled medium. If it falls at 15 or higher, I want to label it high. Okay, so I'm going to indicate that with an if-else statement. So I'll say if else the element in row I column 2 is less than 10, then I'll assign the element in row I column 3 to be low. So I'm creating a new column. These columns are my coded values. Okay, and then if else, then if the value in the second column of row I is less than 15, okay, then I'll label it medium. Otherwise, finally, I'll label it high. Okay, and then I want to increment up my counter. I is now going to be I plus 1, and then close the loop. Okay, and let's give some names to that my new data set, because I've essentially added a column there, and I want to call that third column lot size code, and we'll check it out here. All right, good. So you should see, yeah, okay, 15 and higher is high, less than 10 is low. These are all lows. 21 and high, 21 is definitely high because it's greater than 15. I don't see anything between 10 and 15 there, but I could just if I do PT, yeah, okay, anything from 10, 11, 12, these are all labeled medium, so it looks like the process worked. Okay, so that's good, and we can move on. So to run the Levine test, I need the car package, CAR. Okay, and so I'll load that car package, and then I'm going to do Levine test on the residuals. Okay, from my output. Remember, I already did the linear model, but versus lot size code. This variable here, lot size code, but Levine test wants this thing treated as a factor. This is a variable class. Okay, so I want this thing treated as a factor, and so this will be important for you to put in. If you don't, that will probably work okay too. Sometimes it does, and R may give you a message that says, yeah, this group was coerced into a factor. Okay, it wasn't exactly a factor, but it recognized that it should be, so it manipulated it so that it was. Or you can use the factor function, and it'll convert that set of values into a factor. Okay, it's just a format of data that it wants it in. Okay, so here's my test output for Levine's test for homogeneity of variance. The p-value is like 10 or 11%, so it's probably not sufficient evidence to reject the claim that the variances are the same. Okay, so that is, I could feel sort of okay about saying that the variation in the data off of the regression line is the same as you move left to right. Okay, that the residuals have the same spread outiness in the up and down directions. Another way to do that, oh, and by the way, also something else you could do, maybe you know this, you can make a box plot. You make 3 box plots for the residuals by category. like this. Okay, I just did box plot of the residuals versus lot size code. Okay, so lot size code is a categorical variable, so it splits the data. It knows to partition the data thusly, okay, and then make box plots for each category of the residuals. Okay. Okay, here's another way you could partition your data. I'm going to call this other for it's another way. I'm going to use the cut function. I'm going to cut pt lot size according to these cuts. Okay, negative infinity, or I guess we could use 0 in this case. And this is where you have to get, you have to just kind of know this. I want to go up to 9.999. Okay, if I put a 10 here, R would actually include 10 in the lower group. Okay, that's sort of silly, I think, but that's the way it does. It's not consistent with the way we do intervals oftentimes in statistics, where we have half open intervals and we have the closed side of the intervals on the left and the open side of the intervals on the right. But so then up to 14.999 and then up to infinity. So I have four numbers, 4 or 5 numbers in there. 1, 2, 3, 4 essentially. 4 values in there to make 1, 2, 3 bins, right? And so now I have to tell it what I want my labels to be. And I'll label them something a little bit different just so that we can see that, well, just because. Okay. Like so. Okay, low, medium, and high. Okay. All right, so, and I'll call this other column like ASDF. Why not? Because it's simple. And I'll cbind the my original data set with other. Okay, and if I do head of ASDF, you should see another column there, right? So this way works perfectly. It's much quicker than I think writing a loop, but you can see that the labels are the same. Excuse me. So if I do Levine test and out of residuals versus ASDF other, I should get exactly the same output. I'm still doing Levine's test for the residuals, but I'm carving the explanatory variable value set according to this other category, which is the same as the other partitioning that we had before, just using a different partitioning method. And of course we get the same output for the test.